Okay, well, welcome to the Friday afternoon colloquium. Today's speaker, we're very pleased and honored to have Professor Frederick Ringwald from California State University, Fresno. Actually, you know him well, but I'll go over his academic background briefly. So he did his undergraduate at Northwestern, double major in physics and astronomy. Then he went on to Dartmouth, where he worked on cataclysmic variables, which is actually what he's going to be talking on today. He's held postdoc positions at Penn State, Planetary Science Institute in Tucson, Arizona. He was a research fellow in Keele University, so he has a lot of funny stories about England that he can regale you with. And then he was also a professor at Florida Institute of Technology before coming here in 2000, I think, or was it 2002?
No, it was 2000, Doug.
It was 2000. Okay, good. He's had observations, or he's had grants observations on Hubble Space Telescope, Chandra X-ray Observatory, among many others. He is active in involving students in his research, and today he's going to tell us about identifying cataclysmic variable stars in automated synoptic surveys. Fred, take it away.
Okay. Identifying cataclysmic variables in automated synoptic surveys, the new generation of telescopes coming online that are absolutely gushing data. Therefore, all the young astronomers are learning everything they can about Python programming, data science, and machine learning in order to keep up with the torrent of data that are coming out of them, that is coming out of them. But of course, a word from our sponsor. Fresno State Physics has a vigorous astronomy program with our campus observatory, our projects with Hubble Space Telescope, other NASA spacecraft and observatories worldwide, and of course our remote observatory in the Sierra Nevada mountains, with which I hope to involve 3 of the grad students extensively this summer. Students are welcome to participate in hands-on research on exoplanets, which are planets above the stars, cataclysmic variables, which I'll tell you about today, flare stars, starburst galaxies, quasars, and of course, black holes. These are not my students. These 4 images were taken with this telescope from on campus here. Okay. After many years of rapid development, astronomical instrumentation for observing this vast universe in which we live may finally be approaching adequacy, although I would not bet money on that. If the universe is good at anything, it's good at surprising us. Automated telescopes are nevertheless producing torrents of data, coping with which is a challenge in itself. The universe is very large and very rich. You are unlikely to look carefully at anything without learning something about it. And ever since Galileo's telescopes, whenever astronomers get a new way to observe, they discover lots that is unexpected. This is a tradition in astronomy and is still very much in effect. Synoptic surveys are observations that are made repeatedly over time over large areas of the sky. And this telescope under construction is the Vera Ruben telescope, Vera Ruben Observatory, which formerly had the name the Large Synoptic Survey Telescope. They're proving particularly productive scientifically. One reason is that sustained, repeated observations of billions of objects at once used to be rare. It used to be that astronomers studied one star at a time. Telescope time on major telescopes is usually parceled out in a few nights per astronomer per semester. Observational astronomers are like drug addicts. When they can't get their telescope time, they get violent. So this system evolved in the day of Edwin Hubble, and it's still very much in effect. But the new automated synoptic surveys are giving it a real run for its money. The problem is when you parcel out telescope time on just a few nights per astronomer per semester, any physics that takes more than a week to take place or is present only in rare objects can be missed. This talk will describe an observational method developed by Fresno State physics graduate student Kurt Schultz. He's now finished, for his MS thesis in 2020. He uses synoptic survey data made over time to use the erratic flickering present in the accretion disks of cataclysmic variable stars to distinguish them from related objects that do not have accretion disks. As we'll show you, this method is still not 100% effective, but the few percent of objects that still do get misclassified as cataclysmic variables invariably turn out to be interesting in their own right. So word on where these data come from. Where do our time series data taken over many years come from? One of the reasons why these data, this mode of synoptic observing with synoptic observing, in other words, repeated observing over time of large area of the sky and many, many objects in these large areas of the sky. One of the reasons why this observing mode is getting so much attention these days is because it used to be very rare in astronomy. It was very difficult to get sustained observations over time because, again, of a highly competitive way, telescope time is still parceled out. But old telescopes don't get any bigger as the younger generation of larger telescopes gets larger and larger. So they tend to fall into disuse, and therefore a group based at Caltech basically got a single $300,000 NSF grant, single $300,000 three-year National Science Foundation grant to automate these three telescopes, two of which belong to the University of Arizona on Mount Lennon in the Catalina Mountains, just north of the city, and also a telescope in the Southern Hemisphere at Siding Spring in Australia. These are two of them are Schmidt telescopes designed as wide field telescopes. And the other is a pretty wide field telescope. They're all built in the 1960s. They're all over 50 years old and therefore falling increasingly into irrelevance, because state-of-the-art science tends to get done on the new modern telescopes, which are much larger and much more expensive. So automating these telescopes and using them to observe large areas of the sky and putting these observations online, since they are paid for by taxpayers' money, paid for by National Science Foundation. National Science Foundation is notorious for telling people who get grants from them, if we are going to fund your project with public money, we want you to make your data publicly available. And this group being based at Caltech, gee whiz, you think they might have a decent web programmer or two? They have a really wonderful web page and they make all their data available. It's called the Catalina Real-Time Transit Survey, CRTS. It's named after the where the first two telescopes were situated, still are situated in the Catalina Mountains, just north of Tucson, Arizona. Catalina Real-Time Transit Survey uses three automated telescopes. Again, the two in Arizona and the one in Australia. So three automated telescopes in both hemispheres, both north and south, to scan 80% of the sky. They notice they avoid the plane of the galaxy because the fields are too crowded. And also the original scientific justification for this was to search for near-Earth asteroids, for which it's fairly easy to get funding to observe, because you can always scare people and say, fund my research or you'll be clobbered by a large asteroid, just like the dinosaurs, and they go for that. The point is that near-Earth asteroids, objects in the solar system, including near-Earth asteroids, will be preferentially in the plane of the solar system, in the ecliptic plane, where all the planets are within a few degrees are, the plane defined by the orbit of the Earth around the sun. So they observe in the ecliptic plane most heavily, with a gap for the galactic plane, and also they don't observe at the poles of the ecliptic poles, the parts of the sky perpendicular to the ecliptic plane, but otherwise cover about 80% of the sky. Since then, the new automated surveys are sophisticated enough to be able to measure how stars, to observe stars in the galactic plane. But this was the first of the modern automated surveys, so they did not want the extra complication. The original purpose, again, was to discover near-Earth asteroids, which has been brilliant at. It's also been highly successful at discovering supernovae, cataclysmic variables, etc., because these telescopes observe the sky in long, skinny strips as the Earth rotates from night to night. And as the Earth moves around the sun, they change the declination, in other words, the north-south pointing. So they cover the whole sky, rather 80% of the sky. And in addition to finding near-Earth asteroids, they also measure the stars in the background and the galaxies in the background. The second data release, referred to as CSDR2, contains apparent magnitudes. In other words, observations how bright stars are, how the intensity. Taken repeatedly over 10 years, from 2007 to 2017, on average every 10 days for over 500 million objects. Gee whiz, you think there might be physically interesting information in that? Many of these stars and galaxies have been observed over 300 times. And best of all of it goes into the public domain, just like NASA data, and can be downloaded for free. So it's no big deal for my students and I to download data from this. And Catalina Real-Time Transit Survey, since it started in 2007, has been cited. The original paper by the principal investigator, Andrew Drake, published in 2009, has since been cited over 888 times as of yesterday. For a single $300,000 NSF grant, that comes to about $600 per citation. Usually for astronomical papers, it's about $10,000. So when this became apparent, every observatory director took note and said, hot dang, how can I do that? So they are now doing it. The Pan-STARRS survey started with a much larger telescope, 2-meter telescope in Hawaii, in Haleakala, Hawaii. It's been operating since 2008. We probably should see about what data we could get from them. The Zwicky Transit Facility, many of the same people, because it's Zwicky was a Caltech, and these are Caltech people. And they've taken over the old 48-inch Schmidt telescope at Mount Palomar and observing the entire northern hemisphere of the sky. I think once every 3 days. It's a faster cadence, faster repetition between fields, and covering the northern hemisphere of the sky very well. The Vera Ruben telescope, which I showed you in the first slide, is under construction in Chile to cover the southern hemisphere. It's a specially designed 8-meter telescope, so 8 meters in diameter, much larger than any of the others, capable of observing much fainter. An 8-meter telescope can see not just 8 times deeper than the 1-meter telescopes shown here. It's more like 64 times deeper. It's amazingly deep. And the southern hemisphere, and of course all the good stuff is in the southern hemisphere. It is scheduled to start routine observations in 2024, with first light planned for as early as 2022, as early as next year. It was originally designed by Tony Tyson at UC Davis and called the Dark Matter Telescope, because one of the primary justifications for it, scientific justifications for it, is to observe gravitational lens events, and by doing this, map out the distribution of dark matter, cosmological dark matter in the universe. Well, Tony realized that this thing was going to cost $100 million, and a project that expensive needs all the friends it can get. So it's quickly pointed out that it can observe anything that moves in the sky, such as near-Earth asteroids or Kuiper Belt objects, the snowballs at the edge of the solar system, of which Pluto is one, and not a freaking planet. Get over it. Anything that changes in brightness, such as variable stars, such as supernovae. They've discovered several rare kinds of supernovae with these automated instruments. And of course, cataclysmic variables, which I'll tell you about, which get the name cataclysmic variables because they have outbursts. And it was originally called the Dark Matter Telescope. Then it was pointed out that you could use it for other things other than dark matter. So it's called the Large Scale Synoptic Telescope. They have named it after Vera Ruben, who was nominated for the Nobel Prize for discovering dark matter, and who personally fed me chicken soup when I was getting a cold in the dining hall at Kit Peak during a rainy night when we should have been observing, but it was raining. And that is one of the great things about astronomy. It's a small field. You actually get to meet these people. It's very much a global village. As I tell students, don't be the village idiot. Anyway, what I want to understand, the science I want to understand, is the physics of accretion disks. They occur across the universe in a wide variety of astrophysical contexts. It is therefore a scientific embarrassment that we understand their physics only about as well as we understood the physics of stars about 100 years ago. 100 years ago, we didn't know about nuclear energy. We didn't know why stars shine. We don't really understand why accretion disks shine. Accretion disks are, of course, the interplay between gravity inwards and angular momentum outwards. All stars are thought to have formed in accretion disk, and all planets. All stars are thought to have formed in the centers of accretion disk, and all planets are thought to have formed in the disk themselves. The formation of the solar system, the solar nebula, was an example. It's mostly dissipated now, just the sun and its 8 planets and change. And one of the reasons why we think this happened is we see it happening elsewhere around other stars, star formation and protoplanetary disk, which is a bit of a mouthful, so they're called proplyds. Planets actually forming in disks around stars. Planetary rings, like the rings of Saturn, like this image taken at Fresno State's Campus Observatory. Binary star systems, which I will tell you more about. Also, much bigger things, whole galaxies of hundreds of billions of stars are disk-shaped. Again, because of the gravity pulling stuff towards the center, but the angular momentum, conservation of angular momentum, tending to extrude the disk around the perpendicular to the rotation axis. Also, there is good reason to believe these days that the centers of just about all large galaxies, such as the Milky Way galaxy in which we live, and many others, have big black holes in them, which probably precipitated their formation. The one in the Milky Way galaxy in which we live, and this is similar, it is not the Milky Way, is a normal galaxy where relatively little gas and dust and stars are falling into the central black hole. But active galaxies, such as quasars, have lots of accretion into the central black hole, to the extent that the gravitational potential energy liberated by the stuff falling into the big black hole in the center can outshine the whole rest of the galaxy by a factor of over 1,000. They're the brightest things known in the universe, rather the most luminous things, the most powerful things known in the universe and sustained over time. When does accretion disk play crucial roles in all of these? Binary systems in particular, accretion onto black holes, accretion onto neutron stars, are how we know a lot of what we know about black holes and neutron stars. I wish we understood accretion disks better. We don't. We don't understand why they are disks. We do not understand the fluid friction or the viscosity that broadens them out into a disk and causes the accretion into the central object. We do not understand the dynamics of how gas moves, or rather how particles move in the disk. We cannot calculate what the spectrum of an accretion disk looks like the way we can for stars and nebulae, which are clouds of loose gas in between the stars. One of the reasons being the simplifying assumptions that helped us figure out stars and galaxies do not work in accretion disks. Accretion disks are neither fish nor fowl. There's lots of evidence that there's lots of energy generation at distances quite far from the midplane of the disk, that many accretion disks have bright coronae and even highly collimated jets coming out of their central objects, of which we do not understand. Word of practical advice for the students. Anytime anybody mumbles relativistic electromagnetic tornado, what that means is they don't know. The physics is poorly understood, and they are hand-waving. Okay, cataclysmic variables are a class of close binary stars, close enough for one star to spill gas onto the other. And they are very nice natural laboratories for accretion disk physics. They are close binary star systems. they have a white dwarf primary star. So it's accretion onto a white dwarf. A white dwarf is a burned out cinder that used to be a normal star like the sun. It's now essentially a point mass. And it's not very bright. It's a burned out cinder that used to be a star. And the star that is losing gas to it, that is feeding it through an accretion disk, is not very luminous. It's basically similar to the sun, maybe a little less massive. Neither the mass-losing secondary star nor the white dwarf that is gaining mass are very luminous stars, are very powerful stars. Therefore, it does not take much in a system like this for the accretion disk to dominate the luminosity, to dominate the light. So what we are looking at when we look at an accretion disk is basically the light of an accretion disk. Rather, we look at a cataclysmic variable, what we're seeing is an accretion disk. And another thing is that this geometry is quite good. Mark Garlick, the artist, got himself a PhD in astrophysics before he realized he would rather paint and write. So his paintings, his space art, is some of the best I've ever seen, because he knows what cataclysmic variables ought to look like. And this geometry is accurate. So therefore, roughly 1 in between 6 and 7 cataclysmic variables will be inclined edge on to us, and we will see eclipses. And therefore, we can turn time-resolved data into spatially resolved data. Map out, for example, the distribution of brightness in the disk and temperature in the disk and so forth. This is one reason why we think a lot of accretion disks have hot coronae, because in an eclipsing cataclysmic variable, often the continuum will be deeply eclipsed, but the lines, the emission lines from transparent gas, will be hardly eclipsed at all, therefore indicating a hot corona quite far from the midplane of the disk. Cataclysmic variables show a wide variety of variability from a wide variety of astrophysics. Much of it is on human timescales, from seconds to minutes to hours to days to weeks to months. Much of the astrophysics, wide variety of astrophysics that Cataclysm shows is on human timescales, observable by students in the limited time they have. A student can get maybe a few nights of observations of one of these and turn it into a publishable paper within a semester or two. And it is astrophysically interesting. These papers get read and therefore cited. They must get read because they do get cited. So these are very nice natural laboratories for observing accretion disk physics, and very nice thing for students to do. These light curves that I'm showing here on the right are plots of apparent magnitude, in other words, intensity, as a function of time. And they show a wide variety of variability in the intensity of the light and the power output of these things. This one, for example, you see the orbit going up and down, the sinusoid of the orbit. You also see up and down, rapid up and down variations, because the white dwarf in this system is magnetic and spinning with a period different than that, shorter than that, the orbital period. This one is showing the totally erratic flickering that I will tell you more about later, coming from the accretion disk, coming from its thought erratic magnetic reconnection events in the accretion disk. Here's an eclipsing system. You can see the eclipses every orbital cycle. And before, you see the orbital hump as the bright spot where the gas stream hits the disk, comes into the front. And then immediately afterwards, the secondary star eclipses it, and it goes back into quiescence. So orbital hump, eclipse, orbital hump, eclipse, and so forth. Here is a dwarf nova system where you have outbursts in the disk, unstable mass flow through the disk, causing avalanches of gas inward from the disk, both normal outbursts in this one and also super outbursts. The super outbursts are caused by tides. They happen in short period system. They're caused by tides. And during these super outbursts, you get waves of the disk, which are unfortunately called super humps. Super humps go on to the list of astronomical terms that should not be spoken in public among non-astronomers, because they make them giggle. Like the naked eye, heavenly bodies, double degenerates, heteroskedastic, and many others. I keep a list. This one is Eric Gokin is studying, these have normal outbursts and standstills. The accretion disk apparently is at a critical luminosity, critical mass transfer rate, such that if they hang up in a state resembling being an outburst all the time, this potentially gives us rather precise information about the mass transfer rate and about the accretion luminosity in the accretion disk. And Eric has done the best compilation of statistics on these objects that have ever been done. I can't wait until we publish it. This one has a low state, which were analyzed by Kylie Ford. She did her master's thesis last semester. We really ought to get it into the press because it's the best ever, most detailed examination of these low states. The one thing that all these stars have in common is their secondary star, which is magnetized, which should have big star spots, similar to sunspots, concentration of magnetic fields on the surface. And if you had a big star spot move or form over the L1 point, the spigot point where the mass transfer comes from, you would presumably choke off the mass flow. And to make a very long story short, Kylie has found lots of good evidence for this. This one has the nuclear-powered nova eruptions of gas building up on the surface of the essentially white dwarf that I'll tell you more about. But yeah, these things do a wide variety of things. They're called cataclysmic variables because they have cataclysmic variables, both nuclear-powered nova outburst and gravity-powered dwarf nova outburst in intensity over time. And notice the time scales: 5 hours, 2 hours, 7 hours, 260 days, 500 days. The point is that much of this physics is on quite short time scales, easily observable by students. Cataclysmic variables have cataclysms. That's why they're called cataclysmic variables. Classical novae have nuclear-powered eruptions on the surface of the white dwarf. The white dwarf that is being spilled upon is a burnout cinder that used to be a star. It's essentially a solid. It's technically gas, but the gravity is so strong because the nuclear processes that power the star have ended, that it's shriveled up into this tiny little cinder that is essentially a solid, a very dense solid. And you keep dumping hydrogen-rich gas onto that, it'll eventually build up in temperature and pressure until it detonates in thermonuclear runaway. That's classical nova eruption, because they've been seen since ancient times. Nuclear-powered eruptions on the surface of the white dwarf. Dwarf novae, on the other hand, have gravity-powered outbursts from unstable mass flow through the disk. It is true that they're faint most of the time and that they get brighter, reminiscent to the way a nova does it. But the amplitudes of classical novae are typically tens of thousands. In a nuclear-powered eruption, a classical nova typically gets tens of thousands sometimes brighter than it is when it's quiescent. Dwarf nova, it's typically on the order of maybe 100. And classical novae recur, actually, they're usually seen only to happen once. Some of them recur over decades. But dwarf novae recur every few days, every week or two. And the star is these dwarf novae are always doing something. So amateur astronomers love them. They observe them all the time. We've got wonderful data on them. The brightest dwarf nova has a light curve observed by the amateur astronomers going back to 1892. The last time there was a gap in the data big enough to have missed one of these outbursts was in 1914. And yes, well-trained amateur observers can estimate how bright stars are to within about 10%. Better than old-fashioned chemical film photography, not as good as modern digital techniques, but nevertheless. Cataclysmic variables have cataclysms. Nuclear-powered classical nova eruptions and gravity-powered dwarf nova outbursts from unstable mass flow through the disk. An avalanche inwards, giving you a dwarf nova outburst. Insofar as they don't, nova-like variables have no outburst. And it's confusing terminology, I know, because a nova was defined because it had eruption. A nova-like variable, you might think, would have eruptions. No, they don't have eruptions. But otherwise, they're similar to nova-likes. They have similar component stars and they act similarly. So nova-likes are thought to be novae observed in the centuries between outbursts. They resemble classical novae between eruptions, or dwarf novae stuck in outburst all the time. Because they have no outbursts, nova-like variables tend to be underrepresented in surveys. It's the ones that have these big outbursts that get all the attention. The ones that do not have outbursts, that we may be catching between outbursts, do not get much attention. So, how does one study the evolution of cataclysmic variables since they have such a complex phenomenology, or in other words, they do so many different things? How can one identify an unbiased, statistically complete sample of cataclysmic variables for population studies needed to understand their evolution? My 1993 PhD thesis at Dartmouth College was the first ever attempt at this. All cataclysmic variables do not have outbursts, but they all do have very blue colors from the accretion disk, with ultraviolet light 40%, greater than 40% more intense than their blue light, or in astronomers' notation, U magnitude V minus V magnitude less than minus 0.4 from the hot disk. You have accretion into a disk. As the gas gets closer and closer to the disk, it gets compressed by the ideal gas law. So you can model an accretion disk by a series of rings, the ones in the middle of the disk being hotter. And therefore, they emit a great deal more ultraviolet light in proportion to their blue light, blue visible light, than normal stars do. Therefore, this criterion, U minus B of minus 0.4, excludes all normal stars and includes only cataclysmic variables and similar other accreting objects, which I'll show you in a bit. All cataclysmic variables also have spectra with emission lines, unlike most stars, which have absorption lines. Normal stars approximately fit blackbody curves. In other words, Planck spectra, thermal spectra, because they're dense and they're hot. So they radiate as thermal spectra. Only not exactly. They have spectral lines in them. The reason why is they have atmospheres. Remember Kirchhoff's laws for spectra, that when you take a hot opaque object and put its light through a prism or grating, you break it down to a continuous color, a continuous spectrum of colors. This is what thermal radiation is. Planck radiation, also called blackbody radiation. Transparent gas that is hot enough to make light does not do that. You break its light down into colors and you get only specific spectral lines, an emission spectrum with only specific colors. And since these are such narrow regions of the spectrum, they're called spectral lines. This is how we generate, this is how overhead fluorescent lights work. Transparent gas, thin transparent gas, giving you spectral lines. And since Niels Bohr's modeled the atom, we've understood this as from jumps in the electrons. Well, normal stars are opaque in the inside, but they're transparent on the outside. So normal star has an absorption spectrum, which is essentially a continuum spectrum minus an emission spectrum. And here's an example right here. Spectrum of a star, normal star called Vega, that fits approximately a Planck curve for an object at its temperature, but the spectral lines are from the atmosphere, from light filtered out by the atmosphere. Cataclysmic variables have accretion disks, though, so they have emission lines similar to nebulae, superimposed on bright blue continua from the disk. So the emission lines probably are thin gas above and below the disk, and again, evidence for a hot corona. You show the spectrum of a cataclysmic variable to any astronomer who knows the spectra of normal stars well, and their eyes will just about pop out of their heads because, again, these are very unusual spectra with strong emission lines on a blue continuum from an accretion disk, not from a stellar surface. The Palomar Green, or PG survey, was done by Richard Green on Mount Palomar and published in 1987 by Richard Green, Martin Schmidt, who discovered quasars, who was Richard's PhD thesis advisor at Caltech and put him up to the job, and Jim Labert, who's interested in the late stages of stellar evolution. Published in the Astrophysical Journal's supplement 1986. Here's the bibliographical information. It surveyed about a quarter of the sky down to 16th magnitude for objects with ultraviolet excesses. In other words, U minus B of less than minus 0.4. So the ultraviolet, how bright these stars are in ultraviolet light is brighter than how brighter they are in blue light by about 40%. This was enough to exclude all normal stars like the sun and include only unusual objects. The sun is, in fact, a little brighter in blue light than it is in ultraviolet light. And most stars, even the hottest stars, the very hottest stars, normal stars, have U minus B of minus 0.3. So this criterion excludes all normal stars and includes only unusual objects, such as cataclysmic variables. Nearly all large galaxies, such as Milky Way galaxy in which we live, have supermassive black holes in their centers with masses greater than 1 million solar masses. They're powered by accretion, just like cataclysmic variables are, only much, much bigger, 1 million times more massive. Quasars are the most luminous galaxies. They're powered by gas and stars falling into their central black holes. This accretion luminosity can be over 1,000 times brighter than all the other stars in the host galaxy. The Palomar Green Survey was originally intended to discover enough quasars to measure their luminosity function, in other words, how they evolve over the age of the universe. So Martin Schmidt, who discovered Martin Schmidt, who discovered quasars, put his grad student Richard Green up to the task of gaining a deeper and unbiased survey for this. Out of 1,715 ultraviolet excess objects in the complete survey, the Palomar Green Survey found 114 quasars, over 1,000 hot high-gravity stars, which are dying stars in their late stages of evolution, including white dwarfs and hot sub-dwarfs. Included were 17 objects classified as cataclysmic variables because they had emission lines at velocity that placed them within the galaxy, as Richard Green noted in his paper. So I started my PhD thesis using these for a population study, the first ever population study that can claim to be reasonably unbiased of cataclysmic variables in my PhD thesis. I did detail the spectroscopic observations. Dartmouth still has a very nice observatory in Kitt Peak in Arizona. And again, a word of advice for the young astronomers or for the young grad students of all kinds. You want a PhD thesis advisor to give you essentially unlimited freedom, which I had at an Ivy League school, Dartmouth being Dartmouth, rather unlimited funding, rather, and unlimited freedom, which my advisor gave me. John Thorstensen gave me essentially unlimited freedom. Perhaps a bit too much, because at one point, I call him from Kitt Peak in Arizona, from their observatory, from Dartmouth's observatory. I call him in his office on campus in New Hampshire. And we're talking about the project. He says, yeah, that sounds like a pretty good idea. Why don't you do that? I said, well, by the way, where are you? And I said, oh, I'm on Kitt Peak. He says, oh, are you supposed to be there? So that was great. I did detailed spectroscopic observations of all of these, showed that only about half of them, 38 of these 76 objects, were in fact cataclysmic variables. To do this, I burned up over 130 nights of telescope time over 4 years at Dartmouth Observatory in Kitt Peak in Arizona. Doing this for the new samples of thousands of cataclysmic variables being discovered by today's automated telescopes would at the same rate take a graduate student over 50 years. Completing an astronomy PhD now takes 7.0 plus or minus 1.0 years. Dragging out to 50 years is completely unacceptable. I'm sorry, no. So, can we find a reliable way to tell cataclysmic variables from non-cataclysmic variables that is easy to automate? Well, consider what kind of stars did the Palomar Green Survey misclassify as cataclysmic variables. It was all done manually in the 70s and 80s by Richard Green and Martin Schmidt and Jim Liebert, basically getting one spectrum of each star at a time and classifying them basically by scanning the spectrum and looking at it with their eyes. What kind of stars did the Palomar Green Survey misclassify as cataclysmic variables? And looking at this list, there are two major types. One is detached cataclysmic variable progenitors. These have similar component stars as cataclysmic variables. You have a hot white dwarf irradiating the facing hemisphere of a cooler companion star, creating emission lines, because again, there's a temperature inversion of this gas, so giving it transparent gas and therefore emission lines, giving you a spectrum that looks very much like those of an accretion disk, emission lines in low resolution classification spectra. The intensity of both stars varies smoothly and sinusoidally throughout the orbit. As the cool star goes around the hot star, the facing hemisphere and the emission lines come into and out of the field of view. The variation is nice and smooth and sinusoidal, unlike what you get in the accretion disk of a cataclysmic variable. Accretion disks are erratic. And the second kind of stars misclassified as cataclysmic variables in the Palomar Green Survey were hot sub-dwarf stars. These are hot but dying stars, or hot stars in the process of dying. They have ultraviolet excesses, just like cataclysmic variables, other colors, and continuous spectra that resemble those of cataclysmic variables when in outburst, and therefore can be confused in low-resolution classification spectra. You realize that to get these spectra, Richard Green and company had to get spectra of 1,715 objects. It's no darn wonder it took them 9 years to produce the paper. And I did detailed studies of 76 of them in over 4 years. We want something more efficient than this, because the new generation will be getting us to telescopes, automated telescopes will be getting thousands of discoveries. Most hot subdwarfs are not variable, although some can pulsate, again, smooth oscillations, roughly sinusoidal as the star huffs and puffs because it's dying, not like the erratic variability that you see in a cataclysmic variable, an accretion disk. So how do you find a cataclysmic variable? Look for the erratic flickering from a turbulent accretion disk. The point is that this accretion process is turbulent, and we see plenty of evidence for turbulence in accretion disks of all kinds. What convinced me was getting spectra of these and having them come in every 10 minutes and looking at them carefully to make sure that the observations were going well and seeing noticeable differences in the continuum of the spectral lines. An accretion disk is about as stable as a bowl of jello garnished with a couple of hand grenades. And therefore, this erratic flickering, as the bright spot of the disk is in front, and when this one goes into eclipse, notice that the flickering goes off. So the flickering cannot be from the secondary star, the mass-losing secondary star. It's got to be from the disk because it resumes just after this. So turbulence apparently is an important process in accretion disks. We do not understand accretion disk well at all. Rather, turbulence well at all. Turbulence has been called, why some fluid flows become turbulent, has been called the last great unsolved problem in classical physics. I will concede it is unsolved, and I will consider it is great. It is probably not the last. Convection, magnetohydrodynamics, elasticity all pose interesting problems. But notice here is laminar flow, a candle flame, the smoke from a candle flame, nice and smooth and laminar, like you might take in Carl Runde's class. And then as it cools off a bit, breaking up into turbulence, which is poorly understood. So fluids switch from laminar flow to turbulent flow when their Reynolds number exceeds 2400. No one still knows why. And the Reynolds number is defined as the flow speed times the size of a turbulent eddy, about a centimeter or so for this candle flame, and the kinematic viscosity, in other words, the fluid friction in the fluid. Werner Heisenberg, Lev Landau, and Subramanian Chandrasekhar all won the Nobel Prize, but not for figuring out turbulence, because they all published theories of turbulence that do not work. Andrei Kolmogorov had the most successful theory of turbulence in that he took a statistical approach to find the distribution of the velocities. He didn't try to model the behavior of every fluid element, or in other words, droplet in the fluid. Turbulence is fundamentally a nonlinear phenomenon. What do I mean when I say nonlinear? In physics, the output or dissipated energy of a linear system grows in proportion to time for a constant input rate. An example is water behind a dam. The longer you have water accumulate from a dam, the more gravitational potential energy is stored up. In a nonlinear dissipated system, the output is at first glance highly unpredictable and not correlated with the input rate. And an example is a snow avalanche. You throw a snowball in the wrong place, you get an avalanche. Notice that big avalanches, you get both big avalanches and small avalanches, depending on where exactly the snowball hits. And small avalanches are much more common than big ones, although big ones can occur. Mathematics is still more precise about, is even more precise about this. A linear function f of s has these properties: additivity, f of x plus y is equal to f of x plus f of y, and homogeneity, f of a times x is equal to a times f of x, where a is a constant. A linear system is the sum of its parts. For example, a clock. A nonlinear system may be more than the sum of its parts, such as a snow avalanche. Nearly all systems in the natural world are nonlinear. Nearly everything that we study in physics classes is linear. There is nonlinear astrophysics, and you wouldn't expect it because astrophysical systems tend to be conservative with constant energy and angular momentum. And non-relativistic, many of them are non-relativistic, orbits of stars around the center of the galaxy, or motions of stars, or rotation of moons, that's non-relativistic motion. Speeds are not close to the speed of light, and they're certainly not quantum mechanical. They're big stars and moons, so quantum mechanics does not cause this chaotic behavior. It's the nonlinearity that causes the chaos. For example, when a pair of stars encounter another star in a dense star cluster, you get the complex dance with one of the stars in the binary system being ejected and the two being ejected on the other side. Much like in the 1951 science fiction film When Worlds Collide, when Earth gets clobbered by the interloping planet Zyra, and they build a space ark and move to it. See the movie, it's a good one. Or how the motion of stars through the galaxy get mixed up because the galaxy has a non-spherical gravitational potential because it's a disk, not a sphere. Or like this moon of Saturn's, Hyperion, has chaotic rotation. You cannot predict the rotation 2 months in advance because it's non-spherical, and it's also torqued by the gravity of several other moons. So you write down the differential equation. Although the two-body problem for gravity was one of the fundamental differential equations, Newton's Principia, one for complicated potential for many different moons torquing on this, can be quite nonlinear, and therefore causing the motion to be chaotic. Another thing to keep in mind is scale invariance and self-similarity in fractals. The laws of physics are not invariant to scale, in other words, independent of size. King Kong could not exist because if he were 10 times taller than a normal gorilla, he'd weigh 10 times 10 times 10 was equal to 1,000 times more, since he's three-dimensional. His legs couldn't support his weight and they would break. And this has happened. The tallest person ever recorded in history was Robert Wadlow. He was 8 foot 11.1 inches tall and weighed 439 pounds. He died at a young age from an infection from a badly fitted leg brace, which he needed in order to walk. His legs were simply not strong enough to support his weight. Turbulence, however, is scale invariant. It is an unusual phenomenon that is scale invariant. It's also self-similar, which means that both large and small eddies occur and act at least approximately the same way, as shown in this drawing done by Leonardo da Vinci. It took modern high-speed photography to reproduce this, but yeah, consider, he was Leonardo da Vinci. He had a good eye. And a fractal is a geometric object that is self-similar, in other words, similar to itself on many scales. Many exist in nature, like this. Actually, this is a computer simulation of the tree branches of a fern. You see them all over nature. Benoit Mandelbrot was a mathematician. He never did get the Nobel Prize, but he did great with t-shirt sales and his book on the stock market. As he famously pointed out, clouds are not spheres, mountains are not cones, coastlines are not circles, bark is not smooth, nor does lightning travel in a straight line. We make all these idealizations of physics. We joke about it. Consider the cow is spherical. You know, the old joke in physics. Well, cows are not spherical, and it matters rather a lot, unless you're making hamburger. Okay, live cows are not spherical. So his book, The Fractal Geometry of Nature, talks about the geometry of roughness and the mathematics that he devises to quantify how rough things are. The key to it is self-similarity in space, things happening on both large and small distance scales and time scales at the same time. Why did no one notice this repeating quality of nature until the 1970s? Because we discuss it virtually nowhere in the physics curriculum. Virtually everything we discuss are linear phenomena. And the answer is, people did notice this repeating quality of nature. There's plenty of artwork from ancient cultures around the world showing it. But they didn't have fast computers to iterate and understand it. We see this in rivers, we see this in mountains, we see this in neurons, we see this in blood vessels, we see this in the branching of trees. We see it in the large-scale structure in the universe, and Mandelbrot had a good paper about this, how on the largest scale of the universe, galaxies are organized into clusters of galaxies, roughly 10,000 galaxies separated by big spherical voids. Apparently something in the early universe was bubbling. When the universe was still a hot, dense soup, it was bubbling, and the imprints are still left over. Well, the light curves of accretion disk have self-similar structure too. And Physics 290 student Elisa Lee has recently been calculating the fractal dimensions, or in other words, the roughness of the flickering light curves of quasars, which are active galaxies with accretion disk around the black holes in their centers. Will this correlate with redshift? It may show how active galaxies have been over the age of the universe. Kind of show the black hole mass. Interesting. So self-organized criticality is the subfield. Classical example of being is nonlinear behavior in sand piles, namely avalanches. You pile sand grains up into a pile, they reach a critical slope and you start getting avalanches, both big and little ones. And the little ones are much more common than the big ones. As Per Bach, who thought this up, who thought self-organized criticality, pointed out, why did the Big Bang not form a simple gas of particles or condense into one big crystal? What explains all the structure that we see in the universe? Why is the universe not just a thin soup of hydrogen atoms? How did it clump together? How did things clump together to form stars, planets, and people? And people, in particular, are living. So we needed much more complexity. Where did this complexity come from? It goes against the second law of thermodynamics. Again, against virtually everything that we teach in the physics curriculum. Self-organized criticality needs two things: a continuous energy input source. Therefore, the argument often made by religious fundamentalists that Darwin must be wrong because he goes against the second law of thermodynamics. Well, living things eat food and therefore take in energy. So it doesn't go against the second law of thermodynamics. You have a continuous energy input source. Also, a nonlinear dissipative system. For example, many rough sand grains versus smooth laminar water flow. Or say financial transactions in the stock market. And what gets me about this is this doesn't just apply to physics. This applies to lots of different scientific fields. Benoit Mandelbrot made quite a lot of money with his book on the stock market. Self-organized criticality has two signatures. In time, the presence of erratic flickering, also called 1/f noise, because you find it in electronic circuits too. It's that that you get in electronic noise, good noise, not the that you get when something is broken, or the you get with feedback. And Jimi Hendrix would yell, "Turn that down, turn that down." In space, the emergence of, so self-organized criticality has erratic flickering, and in space you get the emergence of scale invariant, or in other words, fractal structure, repeating scale invariant structure. Parallel distributions are a necessary but not sufficient condition for self-organized criticality. They're a symptom, they're not necessarily a cause. In other words, distributions where you get both big things and the little things are much more common than the big things, like earthquakes or river meanders or neurons firing or the flickering of an accretion disk in a cataclysmic variable. Self-organized critical systems contain very large numbers of degrees of freedom or metastable states, the sand grains being an example here, or financial transactions in the stock market being an example elsewhere. Chaos theory is typically concerned with nonlinear systems with a few degrees of freedom. For example, the double pendulum or the periodically kick rotator. I showed you a double pendulum last time I told you about this. The fundamental difference of self-organized criticality versus chaos is that individual self-organized critical events or avalanches are statistically independent in time or space. In other words, you can have big ones or little ones. And although this motion is deterministic, practically, it's really not possible to predict when precisely one of a given size will be. The best you can do is give a statistical. You can correctly predict the statistical distribution, however. Fluctuations in a nonlinear chaotic system are subject to deterministic time evolution prescribed by a system of coupled differential equations, and thus not statistically independent the way self-organized criticality is. Self-organized critical systems have power law distributions with the number of events as a function of frequency being proportionate to the frequency to the minus alpha, where alpha is greater than or equal to 0, and n is the number of events more common than those of frequency of f. That's a fancy way of saying there are big ones and little ones, and the big ones are much less common than the little ones. Here we go. Again, number of events versus frequency, and actually log of the number of events as a function of frequency. A power law distribution gives you a straight line on a log-log plot of number of events, log of number of events versus log of frequency of the events. When alpha is equal to 0, that's purely uncorrelated white noise, random noise with a mean of 0. When alpha is equal to 1, you get pink noise, also called 1 over f noise, which is common electronics, since electrons do not flow uniformly through wires, and also like the erratic flickering seen in Cataclysmic Variables and Accretion disks. That's actually more of a power law index of about 1.6 to 1.8. Alpha being 2 to 3 is red or brown noise, because most of the power is at low frequencies, like the deep roaring sound of a large rocket, more felt than heard. Another example being thunder. The thunder is very noisy, but it's the deep noise, it's the deep sounds that really get everybody's attention. Fractal geometry applies here. Notice that the light curves of pink and brown or red noise are self-similar, with both large and small features. Both large and small features are similar to each other, like turbulence, river branches, tree branches, blood vessels, nerves, stock market fluctuations, etc. This is from the statistics. This is basically all a result of the statistics of nonlinear systems. And therefore, since it's really mathematics, it's beyond physics. It applies to physics, but it's fundamentally new mathematics made possible by computers. Benoit Mandelbrot was at IBM, and he took full advantage of the computers they had. And accretion disks do this too. And you see it all over the place in the astrophysical universe. Solar and stellar flares have power law distributions where the powerful solar flares are much less common than the not so powerful ones, and in a predictable fashion. Accretion disks do it, meteoroid impacts do it, big events like the asteroid that clobbered the dinosaurs are rare, whereas dust hits are very common, again, plotted in log space. Stellar physics of all kinds, stellar flares, accretion disk, black holes, pulsar glitches. In biophysics, evolution and extinctions, big mass extinctions are rare, little ones are common. Flying formations of birds, big formations of birds are rare, little ones are common. Trees, how trees branch. Also in geophysics, earthquakes, little earthquakes are common, big ones are rare, landslides, forest fires, rainfall, fluctuations of the River Nile, of which there have been records dating back to very ancient times, snow avalanches, human activities, urban growth, city sizes. Notice there are only 3 really big cities in the United States, but a whole lot more small towns, and they follow a power law distribution. Word frequency, short words tend to be used a lot more. Words like at or a or the are much more common than words like supercalifragilistic, whatever it is. Anti-disestablishmentarianism, all right? Traffic jams, little ones are much more common than others. War casualties, let's hope that remains true. Social networks, internet traffic. The point is it's beyond physics, it's math. And I'm over time. I better finish up. In his master's thesis, Kurt Schultz used observations from automated telescopes to analyze the self-similarity of variability of flickering. The accretion disk of cataclysmic variables flicker erratically on timescales from seconds to minutes. It's literally like watching a candle flame. The stars flicker like candle flames with amplitudes of about 10%, timescales of minutes to seconds, and showing self-similarity. Both big and little fluctuations, and the big ones are much less common than little ones. Whatever the case, the physics is poorly understood. Flickering may be due to magnetic reconnection events similar to magnetic solar flares, often referred to as microflaring. I think this is the wrong word. It should be called macroflaring because it's big, and in the accretion disk. Whatever the case, flickering is nearly always present and easy to observe, and easier for students to observe. Kurt measured the parallel index alpha of the light curves of cataclysmic variables from the Palomar Green Survey, observed over 10 years by the automated Catalina real-time transient survey. These 38 cataclysmic variables were the first ever statistically complete sample that I wrote my thesis on. Kurt also measured alpha for 38 other binary systems with similar component stars, but with no accretion disks that had been misclassified by the survey as cataclysmic variables. Kurt's analysis used two methods to distinguish cataclysmic variables, with erratic flickering with non-cataclysmic variables with smooth variability and intensity over time. The first was to simply plot histograms of each cataclysmic variable's variability. Each measurement of intensity was binned by intensity, actually apparent magnitude, with the number of instances of each intensity being counted and plotted. So here's SW Sextatus, a cataclysmic variable with a luminous accretion disk, and it's got lots of flickering, therefore lots of erratic variability, and this gives you distribution, approximately Poisson distribution around its mean. It also goes down real faint because I happen to know this one is eclipsing. A lot of going on with this. Also waves in the accretion disk, unfortunately referred to as superhumps, broadening out this distribution. Here is a star, a normal star that is not a cataclysmic variable, was misclassified by one because it's got similar colors. But notice it's got a really narrow distribution, a little broadening at the bottom due to atmospheric turbulence, but really a much smaller distribution than this. This method detects variability of intensity in any time scale, although it does not distinguish between rapid erratic variability of an accretion disk and other smooth kinds of variability, such as a hot star, such as a white dwarf or sub dwarf, a radiant and cool companion star, or stellar pulsations. Kurt's second method was to measure the parallel index of the variability of the intensity. To do this, Kurt sorted each histogram, which you use Excel to do, just data sort, and sorted each histogram plot by intensity, and then plotting the apparent magnitudes, which are logarithmic way of expressing intensity, versus the log of their rank, the brightest measurement being rank of 0, the highest rank, since log of 1 is equal to, actually 0, since the log of 1, the first rank is equal to 0, and fainter measurements being more frequent. This generates a log n versus log f plot. And wouldn't you know, in an erratically varying cataclysmic variable accretion disk, you could fit quite a good straight line to this with a slope equal to alpha. And here, again, log n versus log f plot. Here's an example of parallel plot and fit for one of the cataclysmic variables. This particular one was a nova-like variable with only the erratic flickering from the accretion disk and no outbursts. Ones with outbursts tend to have discrepant points up here. So we came up with the method of where in this distribution do you fit the parallel. You exclude any outlying points from outbursts. You also output the ankle, which is limited by the fact that these stars are faint and you only get so many photons from when they're at their faintest. So you have this drop off here. And there is a well-defined prescription for doing this. Okay, so here are Kurt's results. The results for both methods for all cataclysmic variables and non-CVs. And confusingly, he put the non-CVs here and the CVs here for the one method, the CVs here. Actually, no, it's fine. Actually, I was looking at it backwards, CVs and non-CVs. Unsurprisingly, the parallel index histogram is a better discriminator of cataclysmic variables, with all cataclysmic that my detailed studies identified as cataclysmic variables, and only 2 of the non-cataclysmic variables incorrectly identified as CVs, as cataclysmic variables. The histogram method, which really only detects variability, misidentified 13 non-cataclysmic variables, but then it only detects variability. Kurt found that the cataclysmic variables with parallel index between 1.3 and 2.92, in other words, rather pink or red noise, the red noise expected from accretion disks. The non-CVs without disk had parallel indices between 1.02 and 1.11, consistent with pink noise from other stereo variability of interest, smoothly varying stereoability as opposed to the erratic variability that you see in an accretion disk. In particular, the 2 non-CVs misidentified as cataclysmic variables by the parallel method are both interesting objects. The hot subdwarf star BG 1710 plus 567 is a rare pulsating subdwarf with an unprecedentedly long pulsation period of 11.0 plus 0.1 hours, as this light curve that I downloaded from the public domain archive from NASA's TESS spacecraft shows. 2 of my other students, Armando Guerrero, who's studying stellar magnetism, actually studying exoplanets, and the magnetism of exoplanets, and Chance Spencer, who's studying X-ray binary stars, are currently using test data. It's really easy to use. There's a real nice web page. You get the data, and it's just so wonderfully clean. It's great because the spacecraft is above Earth's turbulent atmosphere, so you can see these tiny little pulsations, and they're really clean. Typical pulsations for these hot subdwarfs are typically 45 minutes to 3 hours. Finding one with an unambiguous pulsation period of 11 hours, we ought to publish this because the hot subdwarf people will be interested in this. Also, the very hot, over 80,000 DO white dwarf star, PG 0935, the blue one there, plus 087, either has an unseen little companion showing an irradiation variation, or is a rare PG 1159 pulsating variable, because again, it's variable but smooth. We have not gotten a light curve out of it though, because we need to accurately model this visual binary star. Whatever it is, it has a cool visual binary star at a separation of 3.5 arc seconds from it, which Kurt and I serendipitously discovered while looking at the monitor of the computer in my office. We displayed this image and, hey, look at that. Astronomers don't often do that, you know, by discover things by looking at them with just their eyes, you know. You generally need to know something about statistics. Next would be to measure fractal dimensions of the light curve, a third method to measure how rough the light curves are, the way Benoit Mandelbrot said to do it with fractals. Elisa Lee, graduate student working with me now, Elisa Lee can do this with the software she's developed to analyze quasar light curves that I told you earlier in the talk. So it would be a real nice, Elisa is interested in quasars, but this would be a real nice chapter to present these measurements and contrast them in accretion disks around stars and cataclysmic variables with accretion disks at the centers of galaxies around supermassive massive black holes at the centers of galaxies around quasars, and compare them side by side. It's always interesting when you find physics that's similar happening in completely different systems. Like, for example, the mass on the damped driven mass on a spring and the LCR circuit. It's everybody's favorite example, of course, physics 4A and 4B. Also, what I'd eventually like to use is use these methods on the cataclysmic variable from the Sloan Digital Sky Survey, which was done since the Palomar Green Survey. It found over 200 cataclysmic variables, and it may have found many more, which have been missed because of confusion about how exactly do you recognize one of these things when you see one, particularly in large samples. Anyway, I'm way over time. Terribly sorry about that. Let me stop now and ask questions. Or any questions, anybody?
Thanks, Fred. Are there any questions?
So either everybody is too tired or too terrified. I will not claim I was perfect. Everybody is now either too scared or too tired or too scared to move. Oh, sorry.
Good talk, Fred. I have a question for you.
Sure.
Is dark matter involved in any of this, or is basically just gravity and the hot gas, nonlinear dissipative, or what's going on?
Me, no. The last time I did a project with dark matter was the very first colloquium talk, the very first journal club talk I ever gave as a grad student in 1988. I gave it on dark matter. But so I'll answer your question by saying only peripherally. The point is that Benoit Mandelbrot himself had a very nice paper, widely esteemed, well received at the time by cosmologists, basically about the fractal nature of the large scale structure of the universe. On its largest scale, galaxies, the universe is not smooth. It is organized into hierarchically clustered clusters of galaxies. The Milky Way and the Andromeda Galaxy both have little retinues of about 24 galaxies apiece. And this is the local group of galaxies. There are roughly 14 groups of galaxies, the local cloud of galaxies, and roughly 30 clouds of galaxies around the Virgo cluster galaxies, the nearest big cluster galaxies. And the Virgo cluster of about 3,000 galaxies is part of the local supercluster of roughly 10,000 galaxies. And a few years ago, a friend of mine at U of Hawaii, Brent Tully, claimed that he could see evidence for another layer of structure. Knowing his sense of humor, I was dreading he was going to call them super duper clusters of galaxies. Mercifully, he was talked into calling them supercluster complexes, but more extensive, deeper, more unbiased, all digital surveys have shown that was just a statistical fluke. The super duper cluster galaxies do not exist. So the biggest things in the universe are superclusters of roughly 10,000 galaxies. And these big voids, roughly 100 million light years across, in between them, filaments of voids. Apparently something in the hot soup of the Big Bang was bubbling, and this put an impression. And dark matter has everything to do with it. As a matter of fact, the luminous matter that we see, the galaxies that we see, are really the white caps on the water. Really the action here that makes this physics do what it does is the dark matter. But I am personally not involved in that. Sorry.
Oh, good. Thanks.
Okay.
Are there any other questions?
You couldn't say I didn't do a share screen. I didn't do it. I should have done a share. I've had this posted up all the entire time and did not do a share screen here. Share screen, and then what I wanted to do was this one here and this one here. This one, I wanted to show you this one, that frothy structure, the large scale structure of the universe. Superclusters and voids of galaxies, that on its largest scale, matter is not evenly smoothly distributed across the universe. Where did this come from? Why is the universe not just a random distribution of hydrogen atoms, a random thin soup of hydrogen atoms? How did it cluster together into this? Saying gravity kind of misses the point. How did gravity do it? And why does gravity find one region different from another region? That goes against the Copernican principle, you know, that we don't occupy a special place in the universe. So, yeah. So Benoit Mandelbrot had a very nice paper about this. It was well received. And the physics of this is very much due to the presence of dark matter, although I am not involved in this. I haven't done anything with dark matter since 1988. Sorry. Big universe, you know. Anyway, any other questions, or is everybody?
I had a question.
Sure, Gerardo.
Yeah. Do you think there might be any interest in looking at the power in the power law as a function of redshift?
that's one of the things I'd like Elisa to do.
Good.
And since she's working on it now, I will not reveal the results she's getting. She can do that herself well enough. But she's been getting some interesting results about exactly this. Okay. But it's still a work in progress, but nevertheless. And one thing I can tell you is she's now, because of the interesting preliminary results, she's now looking at deeper samples of galaxies. The Sloan Digital Sky Survey, for example, was a largely automated all-digital survey started in the 1990s and still ongoing. It has recorded redshifts of well over 1 million galaxies. Chances are quite good she will not be able to analyze them all. So we need to figure out statistically sensible ways of taking subsamples at different redshifts and doing this analysis. But she is working on it.
Good.
Okay. Any other questions? Notice the first two questions were about cosmology, which is what everybody's interested in these days. I bet you the next question will be about black holes. Come on, let's have it. A word of advice for the students. If you want to make a big contribution to science, an important contribution to science, work on things other people are not working on. The universe is sufficiently rich. You are unlikely to look at anything carefully and not learn something about it. There is somewhat of an art, though, to picking good research projects, because this isn't the same as pick just any old stupid thing and look at it carefully. Pick something that matters, something that people want to know about. But make it something that other people are not working on. New technology, which includes new mathematics, can be wonderful here. New instruments or new mathematics can be wonderful here to do things that people had previously considered too difficult to do or too time-consuming to do. Anyway, are there any other questions?
Okay, well, if not,
Okay.
let's thank Dr. Ringwald one more time. And have a great weekend, everyone.
Yeah, later, everybody.
Thanks, Fred.
Thanks, Fred. Take care.
Later.
Bye.